electronic systems for helping aircraft to navigate is called Tacan, short for Tactical Air Navigation. With Tacan, the ground or shipboard component of the system, a beacon, transmits signals that tell a pilot audibly the identity of the beacon and visually the bearing of the beacon and its distance from his aircraft. A beacon is usually unattended. The range is about 200 nautical miles, line of sight. A single beacon can give distance information to 100 aircraft simultaneously, and bearing and identification information to an unlimited number. Tacan uses the 962 to 1213 megacycle band. An aircraft transmits in the center portion of the band, 1025 to 1150 megacycles on one of the 126 frequencies spaced 1 megacycle apart. In replying to an aircraft's signals, a beacon transmits 63 megacycles away from the aircraft's frequency on the 962 to 1024 megacycle end of the band, the so-called low band, or the 1151 to 1213 megacycle end, the high band. With 126 transmission channels, a large number of beacons can operate in the same area without danger of interference. The first Tacan equipment to be used operationally is the radio set AN-ARN-21 in aircraft and the radio set AN-URN-3 on the ground or aboard ship. In this film, the AN-URN-3 is called a beacon, and we will see how it provides distance, bearing, and identification information to aircraft. To get distance, bearing, and identification information from a beacon, a pilot need only select the channel of the desired beacon. The equipment in the aircraft then automatically transmits distance interrogation pulse pairs. These are, of course, omnidirectional signals, shown here as beam signals for simplicity. The beacon receives these distance interrogation pulse pairs and transmits distance response pulse pairs on its assigned transmitter frequency. The aircraft's equipment measures the time lapse between the transmission of its interrogation pulses and the receipt of the beacon's response pulses, and thus determines the distance between the aircraft and the beacon. Since a number of aircraft may be using the same beacon simultaneously, there must be a way to distinguish each aircraft's pulse pairs. This is done by making the interrogation rate of each aircraft slightly different from the interrogation rates of other aircraft. However, the interval between the individual pulses of a pair is always 12 microseconds for all aircraft and beacons to reduce the effects of noise in complementary receivers. In replying to an individual aircraft's distance interrogations, the beacon responds with pulse pairs having the same response rate as the aircraft's interrogation rate. The meter displaying distance information to the pilot is actuated only by those response pulse pairs having the same rate as that of the aircraft's interrogation pulse pairs. To identify itself, a beacon transmits Morse code identification signals at fixed intervals. When the identification signal is transmitted, randomly spaced pulse pairs used to furnish distance responses are replaced by regularly spaced pulse pairs. The aircraft's distance circuits have sufficient memory to be unaffected by these interruptions. Now let's see how a beacon provides aircraft with bearing information. Let's assume that 3 aircraft are in different positions around a URN-3 beacon, and the beacon is transmitting unmodulated RF signals. The signals that each aircraft receives will be equal in amplitude, regardless of the position of the aircraft relative to the beacon. We can represent the radiation pattern of such signals like this. The amplitude is equal at any given radius in all directions. These signals appear like this on the oscilloscope. Such signals can be used to provide distance and identification information, but not bearing. When a reflector is used in the antenna radiation pattern becomes an off-center cardioid pattern called a limison. Amplitude of beacon signals in this general area is greater than the amplitude of signals in this area. The pattern represents relative rather than absolute amplitudes, since all signals have some amplitude, even in this area. Thus, the amplitude of the signals an aircraft receives depends on the aircraft's position relative to the range. However, the aircraft's equipment can judge the amplitude of the signals it receives only by comparing that amplitude with the maximum and minimum amplitude of beacon output. To make this comparison possible, the reflector rotates around the fixed radiating section of the antenna and, in effect, produces an amplitude modulation of the beacon signal. Now, the signals each aircraft receives are continually going through complete cycles of amplitude from maximum to minimum. Since the reflector rotates 15 times a second, there are 15 complete cycles a second of amplitude modulation, as this oscilloscope representation shows. During one rotation of the antenna, 1/15 of a second, there is one complete cycle of this 15-cycle amplitude modulation. At any one moment, this might be the amplitude of the signals one aircraft receives compared to the maximum and minimum amplitude of beacon output. What we need now is a scale that will translate the amplitude of an aircraft's reception into degrees of bearing. So each time the maximum amplitude of the beacon's pattern is directed east, the beacon transmits a burst of pulses called the fundamental reference burst. To an aircraft directly east of the beacon, this fundamental reference burst is received at the moment the amplitude of the signals the aircraft is receiving from the beacon are at maximum. This point on the scale thus represents a position of 90 degrees relative to the beacon. An aircraft directly west of the beacon receives the fundamental burst at the moment the signals the aircraft is receiving are at minimum amplitude. This point thus represents a position of 270 degrees. All other amplitudes likewise represent corresponding degrees of bearing. When the beacon transmits a fundamental reference burst with aircraft A, B, and C in these positions, receipt of the reference burst by the aircraft would coincide with these amplitudes of beacon output. Position of each aircraft is thus approximately established. When one cycle of modulation represents an entire 360 degrees of azimuth, the slope of the amplitude modulation makes it impossible to read bearings accurately. So, bearings from single cycle modulations are generally accurate only within plus or minus 2 degrees. In order to provide increased accuracy, the URN-3 beacon develops a 135-cycle amplitude modulation in addition to the 15-cycle modulation. Thus, during one rotation of the antenna, 1/15 of a second, we get 9 cycles of the 135-cycle modulation along with the 1 cycle of the 15-cycle modulation. With this 135-cycle modulation, we get a complete cycle of amplitude every 40 degrees of scale, whereas we get a complete cycle of amplitude every 360 degrees of scale with the 15-cycle modulation. In other words, by increasing the slope 9 to 1, the 135-cycle modulation in effect expands the scale, increasing the accuracy 9 to 1. The 15-cycle modulation must be retained for identification of the proper 40 degrees of scale. Thus, a single division on the bearing scale equals 1 degree to the 15-cycle modulation, but only 1/9 of a degree to the 135-cycle modulation. A fixed antenna is used to radiate the signal. As we have seen, this is the radiation pattern produced by a single reflector. This is the radiation pattern produced by 9 reflectors. The combined effect is a scalloped limison. When this is rotated at 900 RPM, or 15 cycles per second, It produces the 15-cycle and the 135-cycle amplitude modulations. Let's see how this aircraft would determine its bearing using the two modulations. When the modulated RF signal is received, the aircraft's equipment first separates out the 135-cycle modulation and determines the position of the fundamental reference burst in a complete cycle of 15-cycle modulation to indicate the approximate bearing. Techniques for performances of this measurement make it possible to determine within approximately plus or minus 2 degrees. The equipment then separates out the 15-cycle modulation. Since each division on the scale is now 1/9 of a degree, the accuracy of this reading is within plus or minus 2/9 of a degree. Why are two different modulations necessary? If the 135-cycle modulation was used alone, the amplitude of the signals an aircraft received at any moment would be at the same point on each of the 9 cycles. The equipment would thus indicate 9 possible positions for the aircraft. But at any given moment, the amplitude of reception can appear at only one point on the single 15-cycle wave. Here, for instance. Thus, the 15-cycle modulation is necessary to find approximate bearing and indicate which of the 9 cycles of the 135-cycle modulation is applicable. One reference burst doesn't allow an aircraft's equipment to check bearing often enough. So in actual practice, a beacon transmits auxiliary reference bursts every 40 degrees of antenna rotation after transmitting the fundamental burst. Now let's watch Tacan in action again, in more detail. This time, observing the part the AN-URN-3 components play in supplying an aircraft with distance, identification, and bearing information. The aircraft's distance interrogation pulse pairs are received at the antenna and passed to the control duplexer, as shown in this block diagram. The duplexer permits simultaneous connection of transmitter and radio receiver to the same antenna. The duplexer channels the interrogation pulse pairs to the radio receiver. The radio receiver sends a single video pulse to the coder indicator for each pulse pair delivered to it. For each pulse to the coder indicator, a pulse pair goes to the transmitter, which in turn sends a pulse pair via the control duplexer and antenna to the aircraft. These distance interrogation reply pulse pairs have the same pulse repetition rate as the interrogation pulse pairs themselves. The coder indicator also receives impulses from the antenna base that trigger transmission of fundamental reference burst trains. A fundamental reference burst train consists of 12 video pulse pairs spaced 30 microseconds apart. Similarly, the coder indicator receives impulses from the antenna base to trigger auxiliary reference burst trains. The auxiliary reference burst train consists of 6 pulse pairs spaced 24 microseconds apart. The number and spacing of the fundamental burst pulse pairs are different from those of the auxiliary bursts, so that the aircraft's equipment may distinguish one type of reference bursts from the other. The impulses that the coder indicator receives originate at a pulsar plate in the antenna base. The plate has one soft iron insert on the top edge and 8 inserts on the bottom edge. As the plate rotates, the inserts pass through magnetic pickups at the top and bottom, causing a total of 9 evenly spaced impulses to go to the coder for each revolution of the antenna. The plate rotates simultaneously with and at the same speed as the antenna reflectors, 15 revolutions a second, 900 a minute. The keyer in the coder indicator sends out the beacon's Morse code station identification call letters. We can now see that the URN-3 signal consists of fundamental and auxiliary reference burst pulse pairs, the distance interrogation reply pulse pairs, and the Morse code pulse pairs that momentarily replace the distance response pulses when the identification is transmitted. When the antenna rotates, the transmitter output is amplitude modulated and produces a pattern which gives this appearance on an oscilloscope. There are 900 reference burst pulse pairs per second, and there are 2,700 distance response or Morse code pulse pairs per second, for a combined total of 3,600 pulse pairs per second. If the beacon receives too few distance interrogations from aircraft to result in the beacon transmitting a total of 2,700 pulse pair responses a second, a circuit in the receiver generates fill-in pulse pairs to make up the difference and so complete the wave form. These fill-in pulses are called squitter. 2,700 pulse pairs are maintained regardless of whether the pulse pairs are distance responses, squitter, or both combined. Now let's review highlights of the URN-3. The URN-3 transmits on the two ends of the 962 to 1213 megacycle band and receives in the center of the band. The beacon receives paired pulse interrogations from aircraft and responds to these interrogations to furnish distance information to the aircraft. The URN-3 provides Morse code identification to the aircraft by replacing randomly spaced pulse pairs with regularly spaced pulse pairs. The amplitude of the beacon output received by the aircraft varies as a result of the reflectors rotating about the beacon antenna. As a result of the rotating action of the reflectors, an aircraft is able to constantly compare the amplitude of its reception with the maximum and minimum amplitude of the beacon output. The aircraft's equipment compares 15 and 135 cycle amplitude modulation with fundamental and auxiliary reference bursts to determine bearing. This electronic system, Tacan, Tactical Air Navigation, furnishes instantly accurate bearing and distance information to aircraft.